I'd like to welcome you to this preview of the IMF's online course on monetary policy analysis and forecasting, or MPAFx. Much of this online course is devoted to examining the structure and uses of a canonical quarterly projection model, or QPM. Models of this type are often at the core of forecasting and policy analysis systems in central banks around the world. In this course, you will learn how to model the dynamics of the main macroeconomic variables: output gap, inflation, nominal interest rate, and exchange rate. You'll also learn the economic considerations behind key behavioral equations in the canonical QPM. We will also walk you through the impulse response functions, or IRFs, a tool which economists typically use to assess the quality of the structure and calibration of a model like QPM. Using the IRFs, we'll examine together the model's responses to a set of typical shocks and contrast them with our economic intuition. The course will demonstrate what to look for in your analysis of the model's IRFs and how to use them to review and refine the model calibration. Together, we will dig into the Kalman filter and its uses in estimating the unobserved model variables such as output gap, real exchange rate gap, and risk premium. You will also get to practice hands-on exercises in MATLAB using the canonical QPM model and a set of ready-to-use model codes. Click on the link below to register for the full course, and if you're interested in learning more about monetary policy analysis and forecasting, I hope you decide to join us.
The MPAFx is really a two-in-one offer. Because on the one hand, it's a crash course in basic macroeconomic theory. So we cover questions like what determines GDP in the short and long run, what drives inflation, the exchange rate, and how does monetary policy fit into all this. On the other hand, it's a very practical course. You get tools like a software environment, program codes, chart packs that central bank practitioners use every day in their work.
This course is particularly relevant and useful for those of you who are central bank practitioners and want to learn and understand practical model building and model operation, and to use this skill in your day-to-day job, either by building your own model from scratch or understanding and approaching the already existing modeling framework.
I truly believe in what we do. We put a lot of effort in this course into our other activities, classroom training, DA projects. The team, myself, we spend a lot of time what I call being on the ground, working directly with the central banks, helping them, participating in hot debates sometimes. I mean, we are dealing with the fabric of what policy modernization agenda is and how to build better central banks.
The inflation equation describes the relationship between the real marginal cost index, the variable RMC, and the headline inflation index. The real marginal costs variable enters this equation with coefficient A2. It also includes the lack of inflation and the expected value of inflation in the next period, which enter with coefficients A1 and 1 minus A1 respectively. We shall see in a minute that the lag and the lead of inflation are a part of the mechanism of how producers reset prices based on how they formulate their inflation expectations. The equation for inflation is also a structural stochastic equation. Hence, it includes the structural shock, which we name the cost push shock. Let's have a look at the real marginal cost index in greater detail. This index is a weighted average of two gap variables, the output gap and the exchange rate gap. We note the following. The components of the index are gaps, the deviations of variables from their equilibrium or long-term trends. It also implies that when the output gap and the real exchange rate gap are closed, their values are at zero. there are no extra inflationary or deflationary pressures associated with costs. The index is a weighted average, with coefficient A3 being a weight of the output gap. The output gap in the real marginal cost index approximates the marginal costs of domestic producers, while the real exchange rate gap approximates the marginal costs of importers. What would be a possible macroeconomic motivation for using the output gap to approximate domestic marginal costs? Consider an increase in demand for domestic goods. In response to this, in the short run, domestic firms will utilize available spare production capacity to deliver larger output. To produce extra unit of goods or services, at some point, firms may in particular need to ask existing employees to work extra hours, or will have to hire more employees. In this situation, the already existing workers may need to be paid more than the usual rate per unit of production. Also, higher demand for extra labor may put upward pressure on wages. Because of such wage pressures, the cost per additionally produced unit of goods and services will increase. Then, firms will need to increase prices to accommodate costs and preserve profit margins, and therefore, domestic cost pressures on inflation will increase. Another reason why the output gap can approximate domestic costs is because when the output gap and capacity utilization increase, then firms use their productive capacity or productive capital more intensively. Therefore, productive capital is going to depreciate quicker, and firms will need to replace capital earlier. To be able to do that, firms will have to allow for higher rates of depreciation and set aside additional financial resources. This extra cost of replacing faster depreciating capital will lead to higher marginal cost of production and higher inflation. The real exchange rate gap approximates real marginal costs that vary with the relative prices of imports. For example, assume that the nominal exchange rate depreciates and that the real exchange rate gap becomes more positive or less negative. The cost of imported goods in the domestic currency equivalent increases. Again, costs will be passing through to prices, which will increase inflation.
Recall that the cost-push shock is part of the Phillips curve. The cost-push shock captures transitory events that impact inflation, such as a hike in the value-added tax. In our experiment, we assumed a 1% shock, so we set epsilon pi t to 1 in the first period of the simulation. I want you to notice two things on the resulting IRF. First, even though the shock lasts only one period, inflation remains high for several quarters. This is due to the lagged inflation term in the Phillips curve that captures inertia in firms' price-setting behavior. A fraction A1 of firms is backward-looking and relies on past inflation when deciding on current price changes. Second, notice that the initial jump in inflation is bigger than 1 percentage point, which is the direct effect of the cost-push shock. This is due to the 1 minus A1 share of forward-looking firms that index their prices to expected inflation. These firms correctly recognize that inflation will be high for a while, so they can increase their prices without losing competitiveness. We have argued that even temporary cost-push shocks can have significant and persistent impact on inflation because of inertia in price setting and revised expectations. What will then, in the end, bring inflation down? Well, it is the central bank's active intervention to achieve its policy goals. As reflected in the monetary policy reaction function, the central bank dislikes projected deviations from the inflation target. In response to higher expected inflation, it will increase the interest rate above the neutral level. The increase will be gradual though, because central banks generally prefer incremental changes in the policy rate, which is captured by the smoothing parameter G1. How will the higher nominal interest rate contribute to curbing inflation? One transmission channel, which we will discuss next, goes through the foreign exchange market. Recall that the nominal exchange rate is flexible and determined by a modified UIP condition that incorporates the risk premium and backward-looking expectations. When the central bank increases the domestic interest rate, demand for local currency assets increases and the exchange rate appreciates in the first few quarters. In our calibration, the nominal exchange rate keeps appreciating compared to baseline for about 3 quarters. Don't forget that a negative change here means a stronger, more appreciated domestic currency. Eventually, the nominal exchange rate will go through a period of depreciation, and in the long run, it will settle at a weaker level than under the baseline. It is actually a useful exercise to show that the nominal exchange rate will be weaker in the long run. However, for the moment, let's focus on the short-run effects of the interest rate hike and the resulting appreciation. How will these affect monetary conditions and ultimately inflation? Well, monetary conditions in an open economy are determined by 2 factors: the level of the real interest rate and the level of the real exchange rate compared to their equilibrium values. We have already seen that the central bank was raising the policy rate in response to the cost push shock. So we may expect that the real interest rate gap becomes positive. However, remember that in our calibration, the central bank is very cautious in adjusting the interest rate. So the rate hikes happen only gradually. Meanwhile, the largest increase in actual and expected inflation happens immediately after the shock. The combined effect of these 2 forces is that the real interest rate is actually expansionary in the first few quarters, and it only turns contractionary after the central bank has completed the tightening cycle and inflation has fallen considerably. But then, what drives inflation down in the first place? Fortunately, in the open economy, we have another transmission channel that operates through the real exchange rate. As we have seen already, the nominal exchange rate appreciates, and this effect is now reinforced by the increasing domestic price level due to the higher inflation rate. As a result, the real exchange rate gap becomes markedly negative, which indicates an overvalued domestic currency. In fact, it becomes so negative that the combined real monetary conditions index signals an unambiguously tight monetary stance, which helps bring inflation down. How? To understand the transmission from monetary conditions to inflation, let's inspect the aggregate demand equation, or IS curve, in the QPM. Tight monetary conditions reduce demand for domestically produced goods. We have seen that in our case, the dominant channel was the substitution away from domestic goods towards imported goods due to the real exchange rate appreciation. The IRF shows us that the reduction in demand leads to a quite persistent negative output gap. At this point, we have all the ingredients to understand the forces that bring inflation and other variables back to their equilibrium values. Let's circle back to the Phillips curve that summarizes the price-setting behavior of firms. Firms respond to changes in the cost of production, which is captured by the real marginal cost variable. Real marginal costs have two components. Cost pressures can be domestic, approximated by the output gap, or foreign, approximated by the real exchange rate gap. Our previous discussions showed that both components decreased after the cost push shock. The negative output gap implies lower cost pressures for domestic producers, while the negative real exchange rate gap signals lower import prices in local currency. These are the forces that bring inflation down over time. Notice that the cost push shock presented a difficult trade-off for the central bank. In order to return inflation to target, it had to engineer a temporary slowdown in economic activity. As inflation gradually returns to target, the central bank can reduce the interest rate back to its neutral level according to its policy rule. With the neutral interest rate, the exchange rate also returns to its equilibrium path, consistent with the UIP condition. The closing of the real interest rate and real exchange rate gaps stimulates an economic recovery so that eventually the output gap also returns to zero. The IRFs in the PDF report confirm that although the cost push shock triggers a lot of movements in the short and medium term, in the long run, all real variables return to their exogenous trend values represented by the zero line.
Let's demonstrate how to detect common issues in calibration of the core equations parameters. The first set of issues are unintuitive responses of variables to some shocks. This is usually best to detect by looking at the impulse response functions. Let's first consider the case of unintuitive direction of reaction of some variable to a certain shock. One obvious reason for observing unintuitive direction of the variable response is potentially the wrong sign of some parameter. To demonstrate this, we can go to read model and change the sign of the effect of the real monetary condition index on aggregate demand. Let's find the parameter B2 and change its value to minus 0.1. We can keep the original value and write the original and new value of the parameter in square brackets. In this way, we can provide two or more alternative calibrations. This will make it easier to compare the impulse response functions for the model with original and modified calibration. We can save the read model file and run script A01 model properties to generate report with impulse response functions. When the script is finished, we should first check that the model has solution and proper steady state for the modified calibration. To check the existence of the unique stable solution, we can simply print out content of variable m in the command window. As you can see, the variable m is a model object with two parameter variants, and both of them have a unique stable solution. To check that the model with modified calibration has the proper steady state, we can print out content of the variable MSS in the command window. There are now two steady-state values for each entry in the MSS. Each of these corresponds to one set of parameter values. Following the order of parameters in the square brackets in the read model, the first values correspond to the original calibration and the second to the modified calibration. As you can see, the gaps are zero. Inflation is at the target, and steady-state GDP growth coincides with its calibrated value of 2.55. Hence, we can conclude that the model with modified calibration has proper solution and steady state. Now, we can open the PDF report called Shocks from the results folder to look at the impulse response functions. Looking, for example, at the effect of the cost-push shock on the output gap, we can see that the reaction of the output gap is opposite to what we would expect. We would expect the negative output gap in reaction to the inflationary supply shock. However, here the output gap goes up for the alternative calibration. A similar unintuitive result we can see in the case of the monetary policy shock, where output gap increases in reaction to the increase in interest rates. The unintuitive direction of variable response can happen if we have parameters with wrong signs. But this is not the only case. Sometimes the parameter values can have correct signs, and yet we can get unintuitive results. Let's demonstrate such a case on an example. Open the read model file again. Remove the parameter value we just added. And consider an alternative higher value for parameter B4. In other words, we will increase the effect of the real interest rate gap on aggregate demand and weaken the effect of the real exchange rate gap. Let's set the alternative value to 0.9 instead of 0.7. We can now save the read model file and run again A01 model properties. Again, we should check that the model for the alternative calibration has unique stable solution and proper steady state. This time, I will let you do it on your own. When done, open again the PDF report Shocks from the results folder. Looking at the reaction of the output gap to inflationary cost-push shock, we see again that the output gap goes up, although this time in the first couple of quarters. The increase in output in reaction to the cost-push shock is again not intuitive. If we see such a result in impulse response function, we would have to revise the calibration. In our case, the problem is the strength of the interest rate channel of the monetary policy transmission to aggregate demand. Because the inflation goes up more than the nominal interest rate in response to the cost-push shock, the real interest rate gap goes negative at the beginning. The accommodative real interest rate gap outweighs in its effect on aggregate demand the restrictive appreciated real exchange rate gap. And as a result, output gap goes up at the beginning. In this case, the solution would be to revise the balance between the real interest rate and exchange rate gaps in the IS curve.